permanent magnet gear wheels. The transmitting torque of the magnetic gear is limited by the maximum power of the magnets. In our case, the coercive force of permanent magnets is 800 kiloamperes per meter. The gearbox consists of two steel wheels with permanent magnets attached to them. Inner wheel we call rotor. Between inner wheel and outer wheel there is a steel stator. The stator is fixed, and in our setup the inner wheel is not rotating. I plan to simulate a series of magnetostatic problems for different position of the outer wheel. For each wheel position the torque will be calculated, and this way we can find the maximum torque that the gear could transmit. Okay, let's start QuickField now. In QuickField I create new problem. Problem name is gear. Next. Problem type is magnetostatics. Length you need some millimeters. Model class is plane parallel, and the model depth is 50 millimeters. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. Here is the file, and I will open it. The model is imported. You can see the cross-section of the gear wheels. Here you can recognize steel parts, permanent magnets, and the air. Let's assign labels. Through labels we will provide physical properties. Switch to Select Objects mode, click the object to select, and type in the label name. This is outer wheel. This is rotor. Now let's zoom in. These blocks are stator. Hold the control button pressed to select multiple objects at the same time. This is the air. Zoom to fit. All permanent magnets feature the same coercive force and are magnetized radially. Therefore, I can assign same label for the inner north magnets. This one, and this one are inner north, and these three magnets are inner south. These would be outer north, and these would be outer south. Now let's provide physical properties for these labels. Double click the label name in the tree, and for the air I specify a relative magnetic permeability which is 1. Okay. Rotor is made of steel with relative magnetic permeability 1000, and the same steel is used for stator and for the outer wheel. Okay. Permanent magnets magnetic permeability is 1.05. The coercive force magnitude is 800 kiloamperes per meter. Magnets are magnetized radially, so I change the coordinate system to polar. And north magnets magnetization direction is outward, so I set here 0 degrees. Okay. And the same for the north magnets of the outer wheel. 105, 800 kiloamperes, polar coordinates, 0 degrees direction. Okay. South magnets feature the same magnetic permeability, 1.05, the same magnitude of coercive force, again the coordinates polar, but the direction is opposite to the north magnet, so I set here 180 degrees. And the same for the south magnets of the outer wheel. 105 polar. Okay. That's all for block labels, but I should also assign labels to the boundaries. I believe that magnetic field is contained within steel parts of the outer wheel, and there is no magnetic field outside, so I assign label to these edges and specify magnetic potential to be 0. Okay. Geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button, save all problem files, and run the analysis. Problem has been solved. Let's take a look at the results. Here you can see the magnetic field lines. You can adjust the field picture and switch on, for example, the color map of the flux density and the vector plot of the flux density. The correspondence between colors and the numbers you can see in the legend. And you can get exact values in any point using local values tool. Just click any point, and here you will get the flux density value, field strength, and other parameters. And you can edit the point coordinates here. You can also use contour tool to get the field distribution along the contour. Switch on the contour tool, change the line type to be the half arc. Before drawing the contour, I will switch off the color map so you can see the contour better. Okay, now click here in the A gap, drag, and then release. Now the contour is constructed, and I can see the field distribution along this contour on the XY plot. Flux density, normal component. And I can get exact values in the table. Coordinates, flux density components, and other parameters. You can also use contours to calculate integrals. Contour clear. Now I will click to select blocks, outer wheel, and the permanent magnets attached to the outer wheel. Follow to the integrals, and here is the mechanical torque, 28 newtons per meter. Let's find the dependence of the torque of the outer wheel position. You can do this manually. Open the geometry model, switch to select objects mode, select outer wheel elements by clicking them. Remember to hold the Ctrl button pressed to select multiple objects at the same time. Now follow to the edit, move selection, rotation by 1 degree. Okay. Build the finite element mesh, solve the problem, use the contour tool to select the outer wheel elements, follow to the integrals, and here is the new value of the mechanical torque. There is a way to automate calculations. QuickField has a label mover tool for parametric analysis. The workflow is simple. Choose the base problem, gear.pbm. Add the values to measure. I would like to make a compound contour, including outer wheel, outer north magnets, and outer south magnets. Okay. And for these objects, I would like to calculate the mechanical torque. Add. Close. Now specify the steps. Record steps. I would like to rotate outer magnets and the outer wheel by 2 degrees. Add step. Close, and I will specify how many times to repeat this step. 20 times. Okay. Now I need only to press Get Results button, and Label Mirror does the rest. The set of problems is generated. In each problem, the outer wheel with permanent magnets is rotated by 1 degree. Then the problems will be simulated and the torque will be measured. Now the problems are being solved, and you may note that several problems are solved at the same time. Now everything is done, and here is the dependency. You can see the plot, how the mechanical torque depends on the outer wheel position. And you can see that the maximum torque is 37 newtons meter. For each intermediate result, you can view the geometry model and you can view the field picture. And if I calculate the torque manually, select the outer wheel parts, follow to the integrals, mechanical torque, you will see that the torque value is the same as in Label Mirror. The intermediate problem files are stored in a separate folder, and don't forget to save the Label Mirror script file. If you search for the permanent magnet gear wheels on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and you can download the simulation files here. The simulation files can be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.